All right, today topic of review is functions that are defined by integrals. So thinking how integrals, again, relates between our derivative, our function, all of that. All right, so on this first one, it says a continuous function f is defined on the closed interval from -4 to 6, and we are looking at the graph of f. Consists of a line segment and a curve that is tangent to the x-axis at x equals 3 and is shown in the figure above. On the interval from 0 to 6, notice they changed that one, the function is twice differentiable. Not the whole time, but from 0 to 6 is twice differentiable, and that your second derivative of x is greater than 0 or positive on that 0 to 6 interval. A, is f differentiable at x? Use the definition of the derivative with one-sided limits to justify your answer. Well, the definition of the derivative is the limit as we look at those. And so if we look at the limit on both sides of our function, as we approach 0 from the left, and using the definition of the derivative, so we'd be looking at the derivative here of the derivative, or the slopes of the tangent lines. So the slope of the tangent line as we approach 0 from the left, that would be this piece right here. The slope of that tangent line, so if I can kind of find some nice points here, we've got a point here at -3, -0, and at 0, 2, so that would be up 2 to the right 3, so it would have a slope of 2/3. So I can find the exact slope on the left-hand side. So then looking at, again, as we approach 0 of the derivative from the right, what are the slopes of that function on the right side of 0? And as we look at the slopes on the right side of 0, the slope of that tangent line, I can't figure out what that is because it's a curve. And so I can approximate, but basically my approximation tells me that it is some negative number. Okay, well, if it has to be some negative number, it obviously can't be positive 2/3. So using, is it differentiable at 0? No. The left and right hand derivatives at x equals 0 are not equal. Part B, for how many values of a from -4 to 6 is the average rate of change of f on the interval from a to 6 equal to 0? So average rate of change, let's remind ourselves, that's your slope formula, and we're supposed to go from some a to 6. So we would have f of 6 minus f of a over 6 minus a. And they want to know how many times does this equal 0? Well, in order for this to equal 0, the numerator would specifically have to equal 0. Okay, or in if we were to solve this, then I see that we would have to find a place where f of a equals f of 6. F of 6 they specifically give us in this picture. F of 6 is 1. So what I'm looking for is how many places, because that's the question, how many values of a can I find so that its function value is 1. So as we look across this picture, here's 1. If I look across the picture, I can see that it would be 1 again right here, and 1 again right here. I don't need to identify what they are, but I can see that it would happen 2 more times. For how many values of a, f of a would equal 1 twice on that interval. So 2 times. Sticking with the same situation, we can move into our mean value theorem. So remember what our mean value theorem is saying, and that is, again, on the interval from 4 to 6, which the mean value theorem was applied. How many times can we guarantee a value c such that a to c to 6 where the derivative equals 1/3. Justify your answer. And that's what our mean value theorem says, is that if we look at that average rate of change on some interval, f of 6 minus f of a over 6 minus a, that it equals our derivative, and they're saying that they want this to equal 1/3. Okay, so what I specifically did on this one is I just looked at the numerator and the denominator here, and I said, okay, well, what would the f of a equal if it were to be 1/3, if this equals 1 and this equals 3, and do those mesh together? Well, if that top part is 1, that means f of 6 minus f of a equals 1. Well, f of 6 is 1. And so I find out that we'd be looking at, let's see, f of a, is 0. So where is our function equal to 0? And it's a couple places here. So then looking at the bottom, 6 minus a equals 3. And do these work together here? 6 minus a at a equals 3. At a equals 3 is our function equal to 0, and it is. And so we can see on this one that we would again have an answer here, and it's saying, is the mean value theorem applied? Yes. On the interval from 3 to 6, it is continuous and differentiable. And that's the requirements for our mean value theorem. All right, on our next one, the function g is defined by, and it gives us an integral, 0 to x of f of t dt, on which intervals contained from -4 to 6 is the graph of g concave up. Okay, well, if g is that function, then that means g prime, its derivative, would be the inside of that, f of x, and its second derivative would be f prime of x. And that's where we would find g being concave up, is where its second derivative is positive. Well, what we have a picture of is f, and we need f's derivative to be positive to make g concave up. So as we look at this picture, we're looking for where are the slopes of f positive, or where is f increasing. And f would be increasing here from -4 to 0. F is also increasing here from 3 to 6. Explain my reasoning. I have a picture of f, so I need to relate g to f, and that is that g's second derivative equals f prime of x, and it is greater than 0 on those intervals. Always make sure that you run the one they're asking you about through the one that you know. All right, on our next one, remembering the relationship again between a function defined by an integral and its derivative. Its derivative is going to be the function. As long as it goes from some number up to x, we can just plug x in. And if it is a plain x, that's all you're doing is plugging it in for the variable t. And so that one of all of these options, if I plug that in, there's nothing else to do because it's just a plain x, so that would match option E. All right, this one takes a little bit of creativity. It says if f of x is equal to 0, the integral from 0 to x of 1 over t cubed plus 2 dt, which of the following is false? A couple things, and I would assume that this problem is non-calculator. And so they ask us both about the function itself and its derivative. But if I don't have a calculator, a little bit tough to do things, but let's look at this first one. If f of 0 means we're plugging in 0 for x, well, that would be the top of that integral, and anything going from 0 to 0, doesn't matter what follows, is going to equal 0. So we're looking for what's false. This is not false. That is a true statement. Okay. And the next one, f of 1 equals the integral from 0 to 1 of 1 over the square root of t cubed plus 2 dt. Okay, now this one's a little tricky, especially if I don't have a calculator. It's a cubed. I don't know, and then this is a really tough one to find the antiderivative of, and I don't need to know what the value actually is, but I need to know if that value is positive or negative. So I thought about, okay, the integral would be totaling up the area under the derivative. So it's totaling up the area under this curve, and that curve is some graph 1 over the square root of t cubed plus 2. Well, I don't know what that graph looks like, but I know that it's something positive or above my x-axis because 1 is positive, and the square root has to be something positive. So whatever this is, whatever this function is, first of all, it has a domain restriction down here, that it's only going to go back here to -2, but it's going to be something above my x-axis. And so if I'm totaling area from 0 to 1, and it's all above my x-axis, that's all going to be positive, I know that f of 1 has to be some positive number. So B would also be true. F prime of 1, and f prime of 1 I can do because, again, we can take the derivative and get that function underneath. So f prime of 1 is evaluating what's inside at 1. 1 cubed is 1 plus 2 is 3, and that would be true. F prime of 1 is 1 over square root of 3. D is going to kind of come back to this idea right here. D would be f of -1. So if I plug that in for x, first of all, we're integrating backwards here, and so we know that we can put a negative and flip our integration and go from -1 to 0. And then this part right here, we already talked about. If we're going all above our x-axis and we're going from -1 to 0, again, I don't know what this graph looks like, but I know if this is -1, my function is somewhere above my x-axis this entire time. This is a positive graph. And from -1 to 0, this would be above my x-axis. So this part of it is going to be some positive value. And then plug the negative in front of it, that's going to be make it a negative value. And so this is what is false. F of -1 is greater than 0. Not true. It has to be some negative value. And then let's just talk about the last one real quick. F is continuous for all x greater than 0. If you just consider the domain restriction of the function 1 over t cubed plus 2, the domain restriction would happen down here, and that is that t cubed plus 2 has to be greater than 0, or let's see, t cubed, or the cube square root of t cubed has to be something greater than the square root of -2. Okay, so we're running into, oops, I don't know why I put cube root of -2. So if they're telling us that t is greater than 0, then it's obviously greater than a cube root of -2. And so that would be a true statement. It's continuous for all x is greater than 0. All right, next one. If f of x equals the integral from 1 to x squared of the square root of t squared plus 3 dt, then f prime of 2 equals. This is one of our chain rule ones. We're going from a number up to a function, which means that its derivative is what is inside evaluated at the top one, but because it is more than just a plain x, we have to use our chain rule. So the first thing we're going to do is just plug in x squared where there was a t, times the derivative of the top bound, and the derivative of x squared would be 2x. Or cleaning this up, going to slide that 2x out front. X squared squared is an x to the 4th. And they ask us to evaluate this at x equals 2. Two times 2 is 4. 2 to the 4th would be 16 plus 3 would be 19, and that would match option A. All right, on the next one, f of x equals the integral from -2 to x squared minus 3x of e to the t squared dt. At what value of x is f prime a minimum? Places that f prime can be a minimum would be the ends of a closed interval, which we don't have, but it would also be at critical points of our derivative. So if I can find f prime and see where it is either undefined or equals 0. So let's look at f prime. F prime of x, again, is we're going from a number up to a function, so I can plug that function in, and we end up with, and I just covered up that problem, it's e to the t squared times the derivative of what we plug in. And we want to know where this is going to be equal to 0. Or undefined, and there is no place that this is going to be undefined. Nothing about this has a domain restriction. But we have two terms here as we think about the zero product property. So we would look at where e to the x squared minus 3x squared equals 0, and where 2x minus 3 equals 0. Well, e raised to something will never equal 0, so we're not going to get any answers from here or any critical points from that strain. But over here, solving for x, we get x equals 3/2. And so as I look at our derivative on either side of 3/2, pick a number over here, for example, x equals 0. If I were to plug 0 in, or look at f prime of 0, which would be this this function right here, and if I plug a 0 in for that, we would get e to the 0, which is 1, times, and then if I plug a 0 in over here, 2 times 0 is 0 times -3. This would be negative. Our function is going to be negative when it's less than 3/2. Pick something greater than 3/2, for example, something like x equals 10. I don't know what e to the really big number is, but it's going to be some big positive number, times 2 times 10 is 20, minus 3 is some positive number, so it'll become positive over here, which means my function, this is the signs of f prime, so it had negative slopes or was decreasing here and then turns around and is increasing. And so I can see that our function would have a minimum at 3/2. All right, last example of a function defined by an integral, and multiple choice questions here. It says the graph of f is shown above. So this is the graph of f of x. And it gives us a function g defined by the integral from a to x of f of t dt. For what value of x does g of x have a maximum? Well, g of x is going to have a maximum, if it has one, at critical points of its derivative. So if we look at g prime of x, that would be at f of x. And so if we look at where that is equal to 0, in the picture above, where is f of x equal to 0, we see that that happens at 3 places, at a, at c, and at d. So if we consider our derivative, which is actually the graph of the picture we have above, and what are its signs, f of x, or our derivative, from a to c is above our x-axis, which means it's positive, and from c to d would be below our x-axis, which means it's negative. So that tells me that g is increasing or has positive slopes from a to c, and then has negative slopes from c to d. So where does it have a maximum? It has a maximum at c.